So hello and welcome to this video on trust region policy optimization. I tried to make a self-contained presentation about this algorithm, so I put in a little bit information and background knowledge about methods from linear algebra, optimization, and information theory. But let's get started. So in the last couple of videos, we actually introduced policy gradients. And in policy gradients, we actually followed the following objective. So we want to optimize the policy, and we want to in other words, we want to find a set of parameters theta that actually maximize the expected return that we can expect from a given policy. What we then actually did is, besides that we introduced value-based reinforcement learning to actually solve this problem, we actually introduced the policy gradient. And the policy gradient is nothing else than derived by a sample estimate where we actually try to improve the probability of actions that actually worked well and decrease the probability of actions that actually worked not that well. So in other words, we defined a so-called advantage estimator or advantage function in here that actually tells us how much better or worse an action is over other actions that we can take in a certain state. In other words, when the advantage function is positive, then the gradient becomes positive and we want to increase this function, and in turn the probability of taking action AT in ST is increased. In respect, if the advantage function is negative, the gradient also becomes negative and the probability of taking this action AT in ST is decreased. And then we actually updated our policy parameters by a simple update rule where we set a new set of parameters theta at a certain time iteration k plus 1 is nothing else than like the current set of parameters in iteration k plus some step size times the gradient of the policy. So we do actually gradient ascend in this step. So to put it on one slide and one algorithm, what we actually do is we are in something like an infinite loop where we keep on collecting trajectories via a given policy pi theta. We estimate the advantage function for each of these steps, and then we compute the policy gradient that actually lets us update our policy parameters theta, and we come up with a new set of parameters theta, and we can start over again and start collecting trajectory via our updated policy. So the question is now, why could this be problematic in practice? And it boils down to the fact that we actually, as we run gradient descent or gradient ascent on one batch of collected experiences, the fact is that the advantage function that we use actually to update our policy is a noisy estimate and might not be correct. Especially in the beginning, it's quite noisy. And the thing is that if we take too large steps in our policy parameters due to the gradient update, this might actually lead to a disaster. So actually our policy might change too much and we will actually end up in a region where we actually have a policy that is performing very poorly. And this can actually also happen if the gradient is correct. On the other side, too small steps are also a bad idea. So if you imagine something like the small trail here, and if you imagine that you perform something like gradient ascent steps in this case, and you're at this point and you want to estimate the gradient, what you actually do is if you take a step size towards the direction of your gradient and the gradient step size is too large, you actually end up falling off this trail. If your step sizes are too low, you might also end up in something like local optima. So in other terms, the definition and the scheduling of the learning rate, especially in reinforcement learning, is a very tricky thing to do, and the underlying data distribution changes with updates to our policy. This is something that we also encountered very often in the last few videos. What's the mathematical formalization of this problem under the hood? So actually, we use first order derivatives to actually update our parameters of our policy, and the first order derivatives actually approximate the parameter surface to be flat, which is not often or not in case that often in practice. Actually, if the surface of our parameters on our policy exhibits a high curvature, it gets dangerous very quickly, and we will end up in problems like on this trail here. And there's another problem that is not that well, that we did not that well cover in the last videos. So actually, you can call it a projection problem. So small changes in the parameter space, so even if you use a small learning rate, such small changes in the parameter space might lead nevertheless to large changes in policy space. So imagine that you only tweak your parameters a little bit. This might actually change the probabilities of certain actions, or in certain states that you would actually select certain actions like immediately, which means that although you make small changes to your policy, to your parameter space, this might lead to large changes in the policy space. In other words, if our parameters theta get updated to areas too far out of our range, actually out of the range where previous data was collected, we have a poor estimation of what happens there, meaning that we will actually end up with a bad policy, and a bad policy leads to bad data, and this might be leading us to the fact that we might not recover at all in the end. Let's maybe begin with something that is called the natural policy gradient, and I will show you a little example what the underlying problem is actually. So this example is actually borrowed from Sergey Levine's course on deep reinforcement learning. So imagine that you have a state space, and the state space is something like a number line in here, which can take actually continuous values. You start at a certain point in here, and your goal is actually to reach this goal state in here. You also have a one-dimensional action space, meaning that you can take either left or right. And we define the reward function to be something like minus the squared, minus the squared position of the state, which is actually the squared distance to the goal, minus actually minus actually the squared number of the action, meaning that you get a penalty if you take large actions. And given that reward function and our definition, we can also define something like a policy. We can define something like a univariate normally distributed policy, which is something having a mean and a variance as parameters k and sigma. And what it's actually doing is with these parameters it defines how to actually move within this number line. Meaning that actually the policy will be something like a Gaussian around the current location, and the action is k times the scale of the policy. And if you do this, we will wiggle around a little bit in here, which will actually at some point, if we have the correct mean variance, lead us to the actual goal position. If we keep on sampling trajectory from it and estimate the policy gradient, what you will see is that the policy gradients will somehow look like this. So you can actually visualize the gradient field of the vanilla policy gradient, and in fact the optimal policy will actually have a variance of 0 and a mean of -1. This will actually be the optimal policy for the given problem. However, what you see is if you actually define the derivative with respect to your parameters, you will see that the gradients actually do not really point to the optimal point in here. And the problem behind this is that the policy with respect to the parameters, actually they have a different scale. The problem is if you actually derive your policy with respect to your your mean and towards sigma, what you actually see is that as sigma gets smaller in your policy from your parameters, which actually what's the correct thing to do, you will see that. So if you derive this with respect to sigma, you will see that you get something like 1 to the power of 4th by sigma, which meaning that this term is getting really large. Which actually means that k as a parameter that's being optimized, it's still there, but actually sigma dominates in your derivatives, meaning that it takes a long time actually to actually correcting for your mean value k, because all the thing you're doing is actually keeping on reducing sigma, because sigma dominates in the objective function. This is also something known from the optimization perspective, where you have a problem that's called poorly conditioned, actually, meaning that your gradient field, and when you keep actually doing something, if you have something like an optimization space, if you have a polynomial optimization function like this, and what you actually want to do is you want to take gradient descent steps to actually come from this point to your minimize or to your optimal point that's actually minimizing or optimizing your function, you will see that there's actually problems or situations where gradient descent actually takes many steps to actually reach the goal, because gradient descent so the optimal gradient descent actually goes towards the gradient direction until it reaches an optimality of this function, and then takes 90-degree steps actually towards this goal. And there is actually a kind of functions that actually exhibit such problems, and it's actually, the thing is behind, so the actual problem in here is that you also have so in this problem, your eigenvalues are actually poorly conditioned, meaning that you have very large eigenvalues and you have also very low eigenvalues. And then this leads actually to the fact that first order gradient descent methods take a lot of steps to actually optimize such a quadratic function in the end. So what we actually want to do in this case is, so I think we understood the problem. And the thing is, what we actually want to do is we want to take something like informed estimation of a step size, which is actually updating our policy parameters, that actually leads us to our optimized position or optimized parameter set quickly. So the question is, how can we actually do this? And if we actually consider the optimization point of view from this problem is nothing else than what we actually do is, if we do first order gradient descent, we're updating our policy with a small step size towards the gradient. And the problem is some parameters change the probabilities a lot more than other parameters would change the probabilities of taking actions. And this means, actually, it boils down to the fact that a single value of alpha as a step size is actually not sufficient to do. We need to somehow reformulate the problem that some parameters are actually updated more than other parameters updated. And what we actually can do, or what we actually want to do is, if you take something like an optimization perspective on the first order gradient descent, we want to actually find a new set of parameters, theta prime, that is actually maximizing the set of is actually maximizing our objective function. But we want that actually to be that what we actually want to do is we want to actually constrain the update of our parameters with respect to some epsilon ball and we around our gradient update. This is actually what gradient descent is doing. We actually estimating the gradient around the local neighborhood of our point, and we want to take a gradient step. And this gradient step is actually constrained by some distance, where we actually can be sure that the gradient is correct. And this distance is something like bounded by epsilon. And so this is actually the thing, but the problem is actually epsilon is bounded by theta, which is actually in parameter space and not in policy space. So what we actually want to do, if we want to reformulate it, because we actually want to not optimize, or we don't want to take step sizes in parameter spaces, but in policy spaces, meaning that we want to take updates within the current neighborhood of our point with respect to our policy, and we want to constrain these updates constraint to some distance between the old set of parameters and the new set of parameters. So we want to actually bound the distance between two policies being updated from one step to the other. And we can actually come up with, actually from this follows actually two problems. The first problem is, how can we actually rescale our steps towards certain parameters, and how can we actually define such a distance function? And such a distance function could be, for instance, the KL divergence. The Cal divergence is something like we will have that in the upcoming slides. The Cal divergence is something like a distance measurement between two probability distributions. However, it's not a distance metric in the vanilla case, because actually it's not symmetric. But we will have a short intro on Cal divergence on the upcoming slides. So if we define something like a divergence between two probability distributions, which is basically what we define here with our policy. Our policy is nothing else than defining a probability distributions over actions, and we want to define the maximum distance that we want to adhere to within our optimization to a certain area where we can actually trust that changes to our policy actually do not lead to a bad behavior of our policy. So we want to actually update our policy, but we want to only update it slightly, where we actually want to trust that the next policy is actually a safe policy that we can keep on iterating through our iterations further on. And it turns out that in the end, if we do something like this, we can come up with the so-called natural policy gradient, where we actually, through a rescaling and through definition of a trust region in here, can actually rescale the gradients to be actually pointing to the optimal goal. So if we actually use Cal divergence, this is then something that's better to do actually with second order information. So first order gradient descent suffers from the problem of actually making the optimization problem locally linear. And if you use something like second order derivative information, what you can actually do is you can actually introduce information about your surface, of the parameter surface, how this actually evolves in space, and you can update your policy with respect to second order information. You see the inverse of the Fisher information matrix, which you will also see in the slides in the end of this talk. Okay, so this is like a very mathematical introduction to the problem and what's the actually underlying problematic of policy gradients is. And now the question is, how can we come up with an algorithm that actually tries to optimize our policy with respect to what we just introduced? Turns out that trust region policy optimization is an algorithm that actually does this. So the simple ideas of trust region policy optimization is basically we want to regularize updates to our policy parameters such that the policy does not change too much. So this is really depending on how does the policy change and not how much do the parameters of our policy change. This is two different things that we actually want to do. So we actually want to limit changes to parameters that are sensitive to the underlying terrain of the optimization space. So 2 slides before, so in this slide, we actually defined something like a trust region in here. So we actually want to constrain policy updates in our surface where we actually can trust that our policy does not change too much, but irrespectively of our parameters. So the idea of trust region methods is nothing new. Trust region methods also were there long before we actually introduced policy gradients. And I want to introduce the idea of trust regions slightly within a few set of slides before we actually start over. If we talk about trust regions, the question is, what we actually do is we talk about optimization. And of course we talk about optimization in machine learning because this is actually what this course is all about. And in machine learning, it is common to formulate machine learning problems as optimization problems. So we could actually minimize the means, the squared error. We can actually minimize the cross entropy. You can maximize the log likelihood or the discounted sum of rewards. Actually, what we do in reinforcement learning. Or if you're doing control, you can actually minimize the sum of your control cost. However, independently of the objective you're actually following, how can we actually do this optimization? And it turns out there's actually there's a bunch of different methods to actually do that, but it turns out that it's actually 2 different kinds of ideas that you can actually follow. The first idea, which is basically something very common to use in machine learning, is the so-called line search algorithms. Gradient descent, for instance, is one variant of line search in general. And what you actually do, you're at a certain point and this is your optimization surface. And what you actually do at that point is you estimate the gradient in actually, which is nothing else than some direction of improvement. Must not be the correct direction of the gradient, but it's just one direction of improvement. And what you then do is you cleverly select a step length, and then you update your parameters so that they actually follow the gradient with respect to your step length. So this is actually what you're doing if you're doing gradient descent. There's a whole bunch of literature actually how to select a good step size and how to select a good direction. You can actually look this up also in some books of convex optimization. So gradient descent is something like the workhorse that you actually use in machine learning. However, on the other side, there's also things called trust region methods. So in trust region methods, it's a little bit different. So in trust region methods, you also have something like a point that is your current estimate. However, you define a trust region around that point. And this trust region is something like an upper bound to your step size, which is actually something like similar to the gradient descent maximum step size length, but you have a trust region around that point. And what you actually do is within that region, you formulate an optimization problem. And what you usually also could do in practice is you could like locally approximate a surrogate function that is easy to optimize within the trust region, and then you update and then you actually optimize your surrogate function in order to update your parameters. Actually, you find a point of improvement within that region. However, it must not be a single gradient descent step or gradient ascent step. Okay, so how do you actually, what do we actually do if you do trust region methods? So how do they actually work? So the idea in general of trust region methods is that you approximate the real objective, so your real surface actually, within a trust region with a much, much simpler objective function. And if you have a much simpler objective function, so f tilde in here, what you then do is actually you solve the minimization or the optimization problem of the surrogate function in here. So you actually find a set of parameters or an optimized point in here, which is actually minimizing your objective function, your surrogate function. Why should you actually do this? Because usually the real surface or your real objective function f is often a very complex function. It could be like a neural network with millions of parameters, which exhibits high curvature and is very complex. However, if you have a local approximation of your function around your point, you can easily optimize this function and take a step, reformulate your problem, and form a new surrogate function of it. However, what's the problem in trust region methods if you use them like here? So if you formulate your optimization problem through a locally optimized or locally approximated surrogate function, the optimum or the optimal set of parameters might be, and you might end up in a region where your surrogate function only poorly approximates your real function. Meaning that your parameters that you actually come up with might be far from optimal because you actually use a poorly approximated version of your real function. And what's the easier solution for that? The solution is that you just restrict the search to region TR, so trust region, where you actually can trust your local approximation to be a good approximation of your function or well enough approximation of your function. And within that region, you actually solve the optimization problem, meaning that all the parameters you want to find are not so far off from your current estimate of your objective function. So how could you actually do this? What you could use in practice, you could, for instance, approximate your complex function locally through a second-order Taylor approximation of your function, depending on the current point estimate C, where you actually are. And so this is just the second-order Taylor approximation around a point that you can just formulate. So you can, there's a definition of the nth-order Taylor approximation of a point that you can actually use to approximate your highly complex function locally. how does this actually look like? So if you have a complex function like something like e to the power of minus x squared, and if you're looking at a point c equal to 1, what you can actually do is you can actually come up and calculate the nth order Taylor approximation of this function. And what you see is actually, if you actually, like in this case, if you just consider the second order Taylor approximation of your function locally approximated onwards from this point, you see that the local approximation of this function is a very decent estimate of your objective function f that is not visible to you. However, it's like much easier to optimize this function, the blue function, instead of the green function. And what you actually see is that at least locally, this function is a very pretty decent estimate, and it really approximates it well in practice. Yeah, what you can then do is, like, you define a trust region as a hypersphere around your point, and you define something like a distance parameter delta that's actually defining the radius of your trust region. And what you then do is, in this case, you optimize your local function, so the blue one locally, find the next best point within your trust region, you go to this point and you make a new approximation locally to your function and you approximate it again, and keep on doing this in iterations, which actually ends up like an optimization procedure that is very well known in practice. Also, for instance, Newton methods works based on this principle behind. So yeah, so how is actually the workhorse of trust region methods defined as pseudocode in general? What you actually do is you define something like a trust region, your initial set of parameters, and your iterations. And what you then do is you loop forever and you keep on iterating on n. You solve your trust region subproblem subject to your trust region parameters, and then you can actually, what you actually could do is you can look how well is your local approximation to your real objective function. And if you see that your local approximation is a very decent estimate of your objective function, you can actually increase your trust region delta. And if you see that they are far off to each other, then you can actually decrease. Delta a little bit. However, what you're actually doing is you're alternating between formulating, solving a subproblem in here and updating your trust region in order to actually converge to a solution where you actually have a good set of parameters x in here. What's the limitation actually of this? The Hessian is actually a quadratic approximation around your point, and we use the Hessian matrix in here. And the Hessian matrix, if you need to calculate the Hessian matrix, depending on your parameters that your objective function actually has, the Hessian is a matrix that's actually n squared, meaning that n are the number of parameters. And if your objective function, or if your function is something like a neural network, and we actually have nowadays neural networks with a million of parameters, then your Hessian might be involving a lot of computational effort to actually calculate the Hessian. As n are the number of parameters and you have n squared entries in your table, you actually need to calculate and store a lot of parameters and actually use that for your optimization procedure. In practice, you can also use something like a first order approximation of your Hessian, and that you can actually do this. However, if you actually only approximate the Hessian, what actually follows from this is that you can only use smaller trust regions as you get an approximation error to your Hessian matrix. Okay, so, and if you actually follow the procedure like this, so you actually have the second order information in here and you make a locally linear second order approximation of your problem, then you can actually minimize your objective function subject to your trust region constraints, meaning that you are at a certain point in here. From here you select the best point that actually minimizes your local surrogate objective. You can take this new point as a point estimate for your new optimization and surrogate function approximation, and you can follow this on and on. It's not that visible in here, but you always select the point that is minimizing your objective function within that trust region. And if you keep on doing that, you can come up with an optimization procedure that actually leads you to the optimal, to the global optimal. However, what follows from it, so if your Hessian matrix is positive semi-definite, you can just do a convex optimization in it. So there's a simple and globally optimal solution that you can actually find with algorithms such as conjugate gradient, which is also part of trust region policy optimization. If H is not positive semi-definite, you have a non-convex optimization problem where you actually can use simple heuristics that also guarantee improvement over the iterations of your optimization. What is positive semi-definite? So actually what you need your Hessian matrix to be invertible in practice, and this means actually that your eigenvalues are all real and positive. Okay, so back to what we actually want to do is, now we talked a little bit about trust region optimization in general, but we want to do policy optimization. So actually the problem of policy gradient is actually that the policy gradient keeps the old and the new policy close in the parameter space, while small changes can lead to large difference in the performance, so in the policy space, and large step sizes might hurt the performance because we might end up with a policy large outside the area we are currently confident with. However, whatever large means, this is up to discussion, and it's not easy to come up with a definition of large. So our general policy graded update procedure looks like this. We collect the trajectories, we estimate the advantage function, we compute the policy gradient, and we update our policy parameters. However, the advantage estimate is not only random in the beginning, we also have a non-stationary input data due to the changing policy and the reward distribution that all changed during the course of training. In other words, we want to update our policy carefully. We want to improve our policy, but we don't want to actually degrade the performance of our policy, because once we are degraded, there's only a low chance that we can actually recover from the degradation. So actually formulating the policy gradient optimization in general as an optimization problem, what we actually want to do is we want to define, so actually what you see here is this is eta of pi, which is actually, we want to actually optimize eta. We want to actually optimize the expected return of our policy pi. And what we do is usually we collect data using our old policy pi and optimize something to actually get a new policy pi. And in fact, so far we didn't really optimize anything. We just favored actions that had a higher advantage in the previous runs of our policy. We just want to make them better. This is actually what we did. And the question comes up is, how can we actually write down an optimization problem that actually allows all that we have learned through trust region methods and things like this? So how can we actually write down an optimization problems that allows us to do small updates on a policy based on data sampled from that policy? So how can we actually use on-policy data and formulate an optimization problem that allows to do small updates? And actually how we can actually do this. This is like building on a very mature paper, actually 20 years ago. And what we can actually do, let's express eta of our new policy pi in terms of the advantage over the original policy pi. And what we can actually do is we can just say, okay, the expected return of our policy pi new is nothing else than the expected return of our old policy pi plus the expected. So if you're actually now sampling trajectories from our new policy, it is nothing else than the expected discounted advantage of the actions that we actually sample from following our new policy pi. So this is actually how we can define the expected return of a policy pi new in terms of an advantage over the original policy. And this means nothing else than, this is actually what I just said. So this is the expected return of the new policy, this is the expected return of the old policy, and this is a sample estimate from the new policy. And we can actually also reformulate this a little bit. This is actually quite the same. So we can up with a new parameter row meaning which is nothing else than the discounted visitation frequency according to the new policy. And if we do this like this, we can then actually take the sum over all of our actions and take the probability of taking an action under a certain state S times the advantage of this action under this state S. And we can actually, if we sum this up towards the discounted visitation frequency according to the new policy, we can actually define the expected return of the new policy in terms of the expected return of the old policy. This is actually an equal formulation. And now the thing is, so this is the new expected return, this is the old expected return. If we can actually guarantee that the advantage of the actions that we took in the new policy are they are actually positive, then we can also guarantee that the new expected return is larger than the old expected return. And this is actually different from what we did so far, because we actually in the beginning we just put in the gradient and updated, and we expected good things to just happen. However, there is an explicit constraint in here that if this is actually satisfied, we can actually guarantee monotonic improvement over the old policy, which is something that we didn't do this explicitly if we just did vanilla policy gradients in the before. So actually, if we guarantee that this is positive, then the new expected return will be larger than the old expected return, and then we can also say that the new objective is actually a guaranteed improvement from pi old to pi new. However, we could formulate the problem like this. However, what we cannot do is doing something like this, because we cannot really estimate the visitation frequency, the discounted visitation frequency under the new policy, because we actually did not sample the states under the new policy. We just sampled so far from the old policy. And so in the current form, we cannot optimize actually this objective function. So, however, it turns out that this is just the formula from here. I put it in the slide up here. But what we actually can do is we need to reformulate the problem so that we can actually have all the estimates. So we have all the estimates from the old policy. We actually sampled the advantage estimates, and we have the probabilities. And what we actually can do, it turns out that we can actually come up with a surrogate function in here that actually locally approximates our estimated return. So the only thing that's actually changing from the original objective function here to the new objective function is here that we just change the discounted visitation counter in here. So because this is actually something we can sample and that we already sampled using our old policy. However, this is not a correct estimate. However, as we see in the idea of trust region methods in the beginning, within a certain trust region, so if our policy doesn't change too much, we can also say that the discounted visitation frequency between the old and the new policy, they are locally very, very, very well approximated. However, this just only requires that delta is chosen based on something like a lower bound approximation error that we need to estimate in order to actually see how much our two policies now differ from each other. So this is actually what we already sampled. So we have this. Now we actually sampled using our current policy all of these parameters, and we can just formulate an optimization problem using the data we just sampled. And what we still need is we need our trust region, which is defined using our step size delta. And this is nothing else than we want to choose delta such that the updates to our policy are still very well locally approximated with our discounted state visitation frequency. If we can come up with a factor like this, if we can come up with a delta parameter like this, we can actually guarantee that our new policy is a monotonic improvement over the old policy. So actually that the policy is improving, and we keep on iterating using this procedure, we can actually guarantee a monotonic improvement to our policy. However, only if we stay within that green region. If we update our parameters towards the red region, we cannot actually, the bet is off actually, and we cannot really guarantee that the improvement is still there. Okay, so if we want to optimize our surrogate function L instead of our real expected return eta, with a guarantee of monotonic improvement on eta nu, we need the bound. So we actually need to bound our updates somehow so that we can actually guarantee this monotonic improvement to actually not degrade our policy. Turns out, also building on very mature work from 20 years ago and covering up using within trust region policy optimization, it turns out that there exists a bound. And the bound that we can actually use is we can actually formulate our problem, and we can actually say that eta so the expected return of our new policy is always equal or greater than our surrogate function of our, so the approximated expected return of our new function minus some penalty coefficient in here. And this is something like what you see here is this is the KL divergence. So basically what this meaning is that we penalize or actually that so we actually can prove that there is a bound that our local approximation of our policy, our expected return of our new policy minus the KL divergence between the old and the new policy is actually bounded by a parameter C, which is actually meaning that, which is actually defined like this. And there's actually proof that there is a parameter set that actually satisfies the following bound. In other words, it depends on the KL divergence between the two policies, and if you see if the KL divergence becomes too large, this is actually not really guaranteed anymore, and this is actually the parameters that penalize this objective. Okay, so this is actually also what we have seen before. We have a difference between two policies, and the difference between two policies can be described by the KL divergence between those two policies. A policy is nothing else than the probability distribution over actions given a certain state, and if we want to define the KL divergence between two policies, or if we need the KL divergence, if we need to derive the KL divergence between two policies, let's just introduce what KL divergence is for all of you actually who are not familiar with that. Every one of you who actually has some basic knowledge about KL divergence, entropy, cross entropy, and information can actually skip and fast forward the video a little bit. So what is KL divergence? KL divergence is nothing else than a measure of distance, so it's not a distance metric, but it's a measure of distance between two probability distributions P and Q. And it's defined like this. The KL divergence between P and Q is nothing else than a sample estimate. So actually you sample points from a probability distribution P, and it is the log probability of this point under the probability distribution P divided by the probability under the distribution Q. And if, as you are in logarithm space, you can actually just subtract these two terms from each other. And what's the intuition behind? So the intuition behind actually stems from the theory of channel coding. And in channel coding, you actually talk about information. And the amount of information so expressed in terms of bits or nets or natural units, is actually so the amount of information that is transmitted from a sender to a receiver actually depends on the actual probability of the event, of the incident that you're actually transmitting. And this means, so actually if you get from a probability distribution a sample estimate, the question is how much information did you actually gain from that sample estimate. And it turns out that the information of a point is x is nothing else than the logarithm from some basis a of 1 times the probability of that point. Meaning that the information of this incident or this event is actually minus logarithm to the base of a of the probability of this event actually happening. making two examples out of it. So just imagine that there is two events, A and B, and A has a probability of 75% of happening, and B has a probability of 25%. And the question is, how much information is this actually if you see A? And it turns out that the information that A has is actually minus log to the power of 2, so in bits, of 0.75. It's actually 0.41, and the information of B is actually 2, which is actually something that is very obvious because the probability of B happening is much, much lower than the probability of A happening. So if someone tells you that B has actually happened, this provides much more information to you than if someone tells you that A happened, because actually you would assume that A happened anyway. Another example is actually if A and B are actually equally likely, so both of them have a 0.5 probability of happening, then the information about which of them actually has happened is minus log to the power of 2 of 0.5 is actually 1. So if you're actually using base 2, this tells you nothing more than how much information is actually, how much uncertainty is actually cut off by half if you get this information. For simplification, usually we use nuts instead of bits because actually you can convert the logarithm of one base to the other base because log 2 is just a constant. So you can just reformulate everything and usually use nuts instead of bits. So if you have the definition of information, you can also come up with the entropy. The entropy of a probability distribution is actually given by this term. Usually entropy is something defined over h, so the variable used to call it is h, and the entropy measures actually the average amount of information that is given by one sample drawn from the underlying probability distribution P. So it actually defined over the whole distribution and all the events that actually can happen. So if you have a probability distribution, it measures the average amount of the information if you just draw one sample from that probability distribution. In other words, it measures how unpredictable your probability distribution is or how unpredictable your sample is. Also stemming from this intuition, it also defines the lower bound to your optimal bit encoding, which many of you actually might have heard in computer science basic classes before. You can also write the entropy of your distribution in its expectation, and you can draw a certain a certain sample of x. If you draw it from P, then you can define it in the expectation. And if you just reformulate it, you just come up with a sum over here. And now, if you're talking about two distribution, you can also you can come up with the cross entropy. So the cross entropy is actually defined as the average number of bits to identify a sample event of some probability distribution P, but if it is encoded using Q rather than P, which is actually then something like this. So the cross entropy between P and Q is the negative sum of the weighted probabilities of sampling Q and encoding it with Q and sampling it from pi. And this tells us the difference about the true probability distribution P and the predicted probability distribution Q given the encoding. If P and Q are equal, then the cross entropy becomes the entropy in this case, because they are actually both the same values. And you can also write the entropy P and Q in its expectation, as we also did in the previous slide. So now we are really like close to defining the KL divergent, and it boils down to the fact that the KL divergence tells you actually how much far away the cross entropy is actually from the entropy. So what you actually want to do is, we want to actually, if you have two probability distributions and they are equal, then we just said that the cross entropy becomes the entropy. And the KL divergence defines actually how much the cross entropy is off from the entropy, which is actually given here. So how much is the cross entropy minus the entropy? And if you just calculate this off, you actually come up to the KL divergence that we defined 3 slides before. You can also define this in continuous space without discrete events in here. Turns out that if you boil this down, you can also see that if you just move around P and Q, you will also see that this expression is not the same expression as before. So the KL divergence is not symmetric, so it's asymmetric, and hence you cannot use the KL divergence as a distance metric. Okay, so that's as a primer for KL divergence and information theory. Now back to where we actually came from. So we talked about incidents and events, and this is also something that you can now use for our action distributions. So if we have actually a discrete action setting, you would have something like discrete probabilities of taking an action in a certain state. This is according to your old policy. This would be according to your new policy, and you can come up with something like a difference. And this is something like a divergence in here. And if you have something like a continuous state space in here, where you define your actions given a certain state as a probability distribution, then you just measure the difference between these two action distributions given a certain state, as in your policy pi. So this actually defines the divergence between your two policies at a certain state. Okay, so back to where we actually were. So this is actually the function that we want to optimize. So we want to find a monotonic improvement from our old policy to our new policy, and we want to optimize this function. And turns out that so we can actually formulate this function, and what we actually want to find is we want to find for this function the parameter or our policy pi that actually maximizes this function, given the constraint to see that our KL divergence is bounded to some degree so that actually our monotonic improvement still holds in this case. So we want to actually find the set of parameters for our policy pi that actually maximizes this objective function. And now, as we now optimize in iterations, what we can actually do is we can actually come up. Let's just define this objective function with our surrogate functions. So what we actually want to do is we want to find surrogate functions that are actually lower bound our objective function, which is the actual expected return eta, and we want to always find surrogate functions that are actually lower or equal to our actually expected returns. So this is actually this function. So if this is the actual function in here, we want to find surrogate functions in here that are actually lower bounded to our function, and we want to find our policy parameters pi that actually maximize this function, and then we can say that we have a monotonic improvement in our surrogate function, but we are still lower bounding really our actual expected return. So if we define a surrogate function in here, which we will see in a minute how to do this, we can just run an optimization and optimize this much easier surrogate function in here, find a new policy, set of parameters pi y in here, so the second iteration, take this point, optimize the surrogate function that starts at this point, and we can go on and do it something like this. So this is actually the basic idea to optimize the actually expected return through optimization of surrogate functions in Trpo. However, it turns out that there's a thing that's still open, because it's actually very hard to optimize the parameters in here, because if you see that, so this is actually the discount factor, so if the discount factor becomes close to 1, this thing becomes close to 0 in here, leading to very, very large C values, which is actually hard to optimize. So this is still something left to open. How can we actually come up with a good set of parameters in here? Just a side note, you can also formulate this problem not with a penalty in here, so this is actually a penalized problem. You can also constrain the problem. Then you say that you want to optimize a locally approximated function in here, such that the KL divergence is below some thresholds, which is actually, from an optimization perspective, allows larger step sizes, but is harder to optimize in practice. Okay, so how can we actually solve the KL penalized problem directly? So now do not talk about policies anymore. I just put in the parameters theta in here. How can we actually optimize this problem? So we actually formulated the surrogate functions, but how can we actually come up with the surrogate functions and how can we actually optimize them? Turns out that we have one thing that's still open to do. We have the maximum KL divergence in here because we want to actually constrain the updates to the maximum KL divergence. However, turns out that if you're doing optimization, it's always a bad idea to optimizing a max. So just use we just use the mean KL divergence instead, because this is much more convenient to actually optimize in practice. Why? Because you have also like outliers to certain states, and you want to not always stick to these outliers. So optimization of a mean is much easier in practice and much smoother in practice. Okay, so this is the very complicated, well, not very complicated, you see it in a minute, function that we want to optimize. And if you remember actually what we explained in the beginning, we make local approximations to our functions. So what is actually L? So actually L is what we actually do with L is it's nothing else than a linear approximation. We do a linear approximation of our L. So if you remember, L is something like the direction of improvement, which can be really described by a linear approximation in here. So we will make a linear Taylor approximation of our surrogate function in here, and we make a quadratic approximation of KL divergence in here. KL is something like bounded to your trust region, because we actually wanted the second order approximation to define something like a trust region around our parameters, which is actually why we're doing a quadratic approximation of L. Turns out, so if you do something like this and you can derive it, and you can this is just a reformulation of this, and you can come up with this optimization formula. You do not really need to understand the derivatives in principle. Turns out that if you're using this function, you make a linear approximation to this term and a quadratic approximation to that term, you end up using this formula, and you can actually draw out the gradients in here. So the first order gradient in the Fisher information matrix, which is something related to the Hessian that you also saw in the trust region methods. And what you now actually want to do is, in order to find the argument that's maximizing the set of parameters that actually are maximizing these functions, what we usually do is we derive our objective function with respect to the parameters, and we set this objective function to 0. So this is just the term that we had in here. I just did just draw out this ones because they're actually making things only complicated in here. And turns out if you derive your objective function with respect to your parameters theta and you set them to 0, you actually end up with this one. And some of you also might have seen this optimization, because this is actually something very similar, or actually similar to what Newton's method is doing. So I actually mentioned Newton's method when I introduced trust region methods in the beginning, and this is actually what you're doing here. You're doing a second order iterative optimization procedure of your objective function using second order information in here. So you take iterative gradient steps with information about second order derivatives on your parameter set, and you can then come up with a new set of parameters where you can start over again and keep on following your gradient information. However, one thing just to mention, I mean, this is just side notes. I think the main details of the algorithms are I have also already presented. Just two minor things also to mention. So the update step in here, actually to come up from the old policy to your new policy, actually involves computing the inverse of your Hessian matrix in here. And I also told you in the beginning of this lecture that the computation of the Hessian matrix itself is very complicated, because the size of the Hessian matrix is n squared, with n being the number of parameters in your neural network. And this might be too expensive for a large set of parameters, which you usually have in practice. What you can do is, or what the authors provide actually to do, you can use the conjugate gradient methods to actually calculate or compute the inverse of this function times the gradient implicitly without actually forming the Hessian matrix or the Fisher information matrix explicitly. In other words, the conjugate gradient actually solves this problem without explicitly formulating the Hessian in the first place. And after k iterations, actually, some numbers of iterations, actually, conjugate gradient actually minimizes your objective function, and you can use conjugate gradient actually to calculate this point. Okay, before I present the pseudocode to you, just some high-level summary of TRPO. So there's actually two ways to formulate your optimization problem. The first one is the unconstrained problem. So you just find the parameters theta that maximize your objective function, which is the surrogate function minus the bounded KL divergence of your new policy to your policy. You can also formulate it as a constraint optimization problem, where you actually want to find the maximize your surrogate function L or your parameters for your surrogate function L subject to a KL divergence constraint, where the KL divergence is constrained by your trust region delta around your current point, where delta is something like a hyperparameter that you usually remain fixed over your learning process to find your actual optimized point. Okay, what you actually do is you solve a constrained quadratic problem using the inverse of your Hessian times your gradient, and then you rescale to get your correct KL divergence. This is something I will not. So if you are interested, you can follow the papers I mentioned in the paper. But this is basically two additional things that you actually do to rescale your gradient updates. So this is TRPO on one slide. I think TRPO is a very mature and optimization driven policy optimization algorithm. What you see here is you see what you have also seen in policy gradient so far. So you collect a set of trajectories, you compute the rewards to go and the advantage estimates that you also use to update your value function, and then you estimate the policy gradient like in the beginning. Then you use conjugate gradient to actually compute actually x, where h is the Hessian of the sample KL divergence. And then you actually update your set of parameters using backtracking line search as we did in the beginning. Okay, and then finally, if you did your optimization in here, so you do this over iterations too, so you actually follow certain steps over your trust regions, and if you converged at this point, so the KL divergence constraint is actually exhausted, you fit your new value function, and then you actually start over again, sample new trajectories, and formulate the surrogate optimization goal, and keep on iterating on it until you start over again. Okay, so I mean, this is TRPO is a very theoretical algorithm, but what's the intuition or the summary of TRPO in the end? The idea of TRPO is actually that we approximate the expected return using a much easier local approximation around our current policy, and this so the assumption of this local approximation is actually that the accuracy of this local approximation decreases when the new policy and the current policy diverge from each other too much. However, we can actually establish an upper bound on this error, and we can hence guarantee a policy improvement if we just optimize the local approximation within this trusted region. So if we do this, we can actually guarantee an upper bound for this error, and hence we can guarantee an improvement to our policy. However, if we actually leave this region, the bet is off, because actually our local approximations also might not be correct. However, might be also some shortcomings of TRPO in practice. So TRPO still minimizes the quadratic equation to approximate the inverse of the Fisher information matrix, which can be like doing this for every policy can be very expensive in practice still. And usually it requires a large bit of rollout to actually approximate the Hessian correctly around our current point. And usually TRPO is less sample efficient to other policy gradient methods when it is trained only with first order methods such as Adam. So if you just say that we use first order methods instead of second order methods, usually other policy gradient methods are better if you use them with first order methods such as Adam. This because actually these become a significant issue if you train large deep networks, because then actually the computation of the second order derivatives becomes very complex. And yes, so this is not only for me. Trpo is a very complex algorithm that's very hard to understand in the first place. So you really keep on looking at Trpo from different perspectives, and actually at some point then you will come up with intuition to actually understand this. For me, it was also very hard in the beginning to understand Trpo and to get all the side nodes correctly with trust region methods, information theory. So there's a lot of things that actually converge in Trpo that makes it really hard to understand for people that are not that very familiar with optimization techniques in general. And yeah, so actually, if you're interested in reading more about Trpo, there is actually two further reading materials that I can actually encourage you to look at. It's the one thing is the Pascal Popor lecture on trust region methods, and there's also 2 following student presentations of Trpo and PPO, and of course the course of Sergey Levin about advanced policy gradients. Here's also a nice video where you actually also can look into Trpo from a different perspective. Okay, thanks, and see you in the next video.